This unit that we're going to be looking at is A1.1, which focuses on water. And we're going to be looking at the theme of unity and diversity. So thinking about the physical and chemical properties of water, how is it used similarly and differently in different organisms? How does it act similarly and differently in different situations? And then what are the challenges and opportunities of water as a habitat? So initially, we need to understand that water is a polar molecule. And so what that means is that there's an unequal sharing of electrons. Hydrogen and oxygen are covalently bonded, which means they share electrons, but because oxygen has a bigger nucleus, which means it has more protons, it's going to pull on those electrons more, and it is going to cause oxygen to have a slightly negative charge on it, whereas hydrogen will have a slightly positive charge. And that's always bebopping back and forth, so it's not constant. But if you imagine that force or that charge applied across millions, billions of water molecules, then you're going to have a factor that plays a pretty big role in how water interacts. And so between those positive and negative charges, a small bond, weak bond can form, which is called a hydrogen bond. And as the charge disappears, that hydrogen bond is going to also disappear, but it'll form between other molecules. So hydrogen bonding is always occurring between water molecules because of the polarity of it. So water acts as a solvent. It's not a universal solvent because it's not going to dissolve everything in it, but it will dissolve polar molecules and ions. And so things that will be dissolved in water would be things like sodium chloride, amino acids, glucose. Oxygen and lipids are not. A tiny bit of oxygen can go into water as a solute, but lipids cannot. And actually, for lipids to travel in the bloodstream, they have to be covered in a phospholipid layer so they can travel appropriately. But water is the medium for metabolism, and it's where the enzymes are acting in our cells, and it does carry things around our bodies. So a solvent is going to dissolve a solute to form a solution. And so in this case here, you can see the water molecules surrounding two different ions, sodium and chlorine. Sodium chloride is going to be the solute, and water is going to be the solvent. And the ions separate into their respective, the molecule separates into its respective ions, and then the water molecules surround it, creating a shell of water molecules around each ion. And that's going to cause them to remain dissolved. Molecules that are interacting effectively with water are called hydrophilic molecules. They love water. Those are going to be polar or charged molecules, so ions. For example, sodium chloride. Hydrophobic molecules are going to be those that do not interact effectively with water. So those would be non-polar molecules that will be insoluble in water, such as lipids or oils. Water has a few different properties that help it, that are a byproduct of it being polar. So cohesion is one of those things. Cohesion is water sticking to other water molecules, and that's through the process of hydrogen bonding. And in xylem, which is the tube that carries water in plant cells, water is going to be under tension as it rises into the air, and it's going to create those hydrogen bonds between the water molecules, holding the water column together that allows it to rise up the xylem. That can be broken if air bubbles are inserted between the water molecules, and that sometimes will happen when water freezes in the wintertime. However, there's another property called adhesion, which is water sticking to other things, that can rectify these air bubbles. And water, because of its cohesive properties, can act as a habitat for organisms. So you can see this water skeeter here lives on the surface of the water. And the surface tension of the water is caused by that hydrogen bonding. So it is that's what allows this insect to disperse its weight onto the water and remain on top of the water. Adhesion of water is where water sticks to other surfaces because of these other surfaces' polarity. And in the case of plants, it's going to stick to the inside of the xylem. And that's going to help it to crawl up the xylem in conjunction with cohesion. And you can kind of see that happening in this slide here. So the water is going to stick to itself in cohesive strategy, and then also stick to the sides of this tubing. And as the tubing is narrower, the water can rise higher because the forces interacting on the water molecules, even though they're weak forces due to hydrogen bonding, are overall applying a greater force per surface area than in the wider tubing. Adhesion of water also allows water to stick to cellulose, which allows plants to continue to take in carbon dioxide from the atmosphere through their stomata. And capillary action is that the water crawling up a tube. That action is called capillary action. And so that's going to happen through adhesion and cohesion. And then if air does get into the xylem, adhesion is able to refill the bubbles with water so that that water column can be reestablished. So there's a variety of physical properties of water that we need to be aware of. One of them is buoyancy. Most organisms that live in water tend to have a density that are close to that of water, so they don't have to exert a lot of effort to allow them to be able to float. Viscosity is the thickness or fluidity of water. And so greater viscosity is going to mean more friction on the tube and less ease of flow. Water with solutes in it is more viscous than water without. And so in this case, we can see syrup, which would have lots of different sugar molecules in it. And it would be a high viscosity substance, whereas a low viscosity substance would just be water without solutes in it. And then organisms living in air versus water are going to have different energy impact demands because of maintaining their buoyancy, as well as traveling through different materials potentially, or alternatively maintaining their own body, the water in their body, if they're, for example, living in salt water. Water also has thermal properties. These include high specific heat capacity, latent heat of vaporization, and a high boiling point. And so these are caused by hydrogen bonding restricting water movement, which means it takes a lot of energy to raise the temperature of water. So high specific heat capacity is how much energy it takes to raise 1 gram of water by 1 degree Celsius. Latent heat of vaporization is how much energy it's going to take to turn liquid water into a gas. And the boiling point is the temperature at which liquid water is going to turn into a gas. Water is also used for cooling and transport throughout the body. And so most things are transported for animals, not in the xylem, but in the blood plasma. And so blood plasma occupies about 55% of our blood volume, and it's going to be transporting ions like sodium chloride, glucose, amino acids. They're soluble enough to be transported in the plasma. A small amount of oxygen, but that's mostly why we need red blood cells, because they're going to be picking up and dropping off oxygen. And then blood plasma can transport fat molecules as well, but they're going to need a phospholipid membrane monolayer around it in order to transport those fat molecules. And this membrane is called a lipoprotein complex. And inside it, there is cholesterol, just like there is in a phospholipid membrane. And then sweating is going to cool us because it evaporates water And in order to change water from a liquid to a gas requires a lot of energy, and that energy is going to come from the skin. So that's going to cool us down. Some animals do this by panting because they have blood vessels very close to the surface of their tongue. Other animals do it by putting blood vessels very close to the surface of a cooling device, like elephants' ears, for example. So blood vessels are very close to the surface of their ears. If they get the ears wet and then they flap them, then that breeze is going to cause evaporation to happen from the surface of their ears and pull heat out of those blood vessels. So there are molecules that are going to interact hydrophobically or hydrophilically with water. Water is going to stick to other water molecules, but if there is a molecule that is hydrophobic, because it's nonpolar, it's not going to dissolve in water, even though it might dissolve in other substances. Hydrophobic interactions is when water is near, those nonpolar molecules are going to come closer together and form larger groups because water is making hydrogen bonds around it. Water, because of its polarity and the hydrogen bonding, is going to end up having a high melting point, and it's going to have a high boiling point as well. Whereas methane, which is also a gas that we can find in our atmosphere, does not. Methane comes from anaerobic digestion by prokaryotes, and so that means it's not using oxygen, and it is breaking down materials for energy. And prokaryotes are bacteria, so those bacteria can be found in animal guts, swamps, and landfills, and methane has the smell of farts. So water is a polar molecule. It is a greenhouse gas, but it's a greenhouse gas that's been around for a long time and had limited impact. I mean, it heats our planet, but the amount of water vapor in our atmosphere is not changing as much as the amount of methane that is in our atmosphere. Water takes a lot more energy to change state and is much more dense. It is not going to heat up as quickly as methane will. Methane is a gas at room temperature and has a low melting point and low boiling point, and it's going to absorb a lot of heat in our atmosphere, which is why it's problematic that melting permafrost is releasing a lot of methane into our atmosphere. So to summarize, adhesion is when water sticks to other surfaces. Cohesion is when it sticks to itself. Solvents water acts as a solvent for many solutes, and that means it can dissolve those molecules for transport in the blood. And then it takes a lot of energy to change the state or warm up water, which is not true of methane. And so you can see here in the ocean surface, even though our planet is warming up, in the atmosphere, the land surface is warming quite quickly. The ocean is warming more slowly. And that is because it takes a lot of energy to heat up water. And you're probably looking at this image of frozen water here and wondering what's going on with these weird tunnels, but this is methane being released from underground seabeds. And actually you can pop these open and light them on fire. So if you are not going to be doing HL, then you don't need to do this slide, but this is the last slide and is for HL students. So we need to think about the extraplanetary origin of water. Water likely came to Earth due to collisions with asteroids. Currently, there's not enough collisions with asteroids or water in asteroids that we could be adding water to Earth now. But a couple billion years ago, there were a lot more collisions with asteroids. Right now, they're about once every 20 million years, but previously it was a lot more common. And then additionally, asteroids earlier, billions of years ago, had more ice on them. But as they travel around planets and orbit around suns, they slowly lose their water because of exposure to the sun's radiation and evaporation. So Earth's current temperature doesn't allow for water to boil, and Earth has a strong enough gravity to hold gases in the atmosphere. It's lost hydrogen and helium. Just gas giants don't lose hydrogen and helium because they have a much bigger gravity, but Earth has, but it's strong enough to hold water vapor. But if most of the vapor in the atmosphere if most of the water on our planet was in the form of water vapor, then some would be lost into space. Mars seems to have had water, but it may have reacted with the surface minerals early on in Mars's lifetime. Earth doesn't have those same surface minerals, so it seems that the reason that we have liquid water on our planet is because it didn't fly off into space, and also it didn't react with the minerals on our land. So when scientists are looking for planets called exoplanets that could be habitable by humans, they're looking in this area called the Goldilocks zone. And that Goldilocks zone is, it's not too hot, it's not too cold, it's just right. And that's going to depend on a few different factors, but we would want to have water on this planet in a Goldilocks zone. And so that's going to depend on gravity, because without a big enough planet, then any gases are just going to fly off into space. Additionally, it's going to depend on the distance from the sun based on how old that sun is, how big that sun is, and how much radiation that sun is emitting. So there are quite a lot of them in a relatively short, in the Milky Way, but obviously those are very, very large distances. So who knows when we might find a planet that would be habitable other than Earth. All right, and that is it for these slides.